All right, in our first video for section 4.2, we're going to compute some complex powers. So let me give a little bit of space here. We might ask ourselves, what does it mean to raise a complex number to a power? Well, if the power is a whole number, we kind of already know how to do that. So what if we wanted to raise to maybe a complex power? So if we wanted to, say, raise I to the 2I power. And let me remind you some of the things that we know about what happens with normal real numbers. So if I wanted to look at, for example, 2 to the pi as a power, just as a motivating example, that's sort of a weird expression, but we could define this. And pi is like close to 3, so whatever we define, we should be somewhat close to 8. And anyways, so how would you go about defining something like this? Well, there's a lot of different ways, but one of the ways, if you have the exponential and logarithm function, is to see that this is e to the log of 2 pi, right? Because the exponential and log function are inverse functions. And then by rules of logs, that power comes down in front. So provided you can compute log 2 in pi, you can exponentiate that, and that's an equivalent way of representing 2 to the pi. Great. So how can we use that to compute this this I to the 2I? Well, we can do a similar thing. We can look at e to the, okay, what happened? The the exponent came down when we exponentiated base e, and then we got a log of I here. And we computed log of I. We saw that it was, let's see, what did we see that it was? It was, well, it was log base e of the modulus of I plus I times little arg of I, right, little ln, little arg. And then this is going to be e to the 2I. Log base e of the modulus of I is 0, as we saw previously in the last section. And then the arguments of I are pi halves plus 2n pi, where n is any integer. And so let's see, if we multiply 2I with an I, we get e to the negative 2 times pi halves plus 2n pi, where n is any integer. And if we multiply that through, we get e to the negative pi plus 4n pi, where n is any integer. And lastly, we get e to the, let's see, 4n minus 1 pi, where n is any integer. In particular, when n varies, we get different values. Okay? We're going to get an infinite number of values here, actually. As n increases, the exponential function increases, and as n decreases, the exponential function decreases. So all of these values for different n's are all different. Okay? So this is multi-valued, which means if we want an exact value, we're going to have to use a principal value, and we will shortly. But nevertheless, these are the powers. These are the 2I powers of I. All right, let's do one more example. Let's look at 1 plus I to the I, which should be e to the I log 1 plus I. And we computed log 1 plus I already, but let's just write it again. So log base e of the modulus of 1 plus I times the argument of 1 plus I, little arg. So that's e to the I, let's see, this is log base e of root 2, and then this is plus the argument of 1 plus I, we said was pi fourths plus any whole multiple of 2 pi. And then we multiply our I in. So when we multiply it on the imaginary part, we're just going to get a negative of that, plus 2n pi, rather. And then when we multiply it on the logarithm, it's just log base e root 2. All right, and this is as good as it gets. So again, this is for n and z, and for n and z. So again, this is multi-valued. Let's do one observation real quick. And the observation is when you raise a complex number to an integral power, let's use m because I'm going to use n in here in a second, then that should be e to the m log z, which is e to the m times log base e of z plus I arg z. And the argument of z is the principal argument plus any multiple of 2 pi. This is for n and z. That's why I use the m. So let's multiply that m through. So this is e to the m log z plus, or oops, that plus is happening up top, plus I times, and then I'm going to multiply the m through those guys as well. So that's m arg z plus 2mn pi. Now, what do we notice here? We have I times 2mn pi. M and n are integers, though. And so, since m and n are integers, this is just another full rotation. In particular, e, this is all happening within the exponent of e, this is going to be, periodic. So this term here doesn't actually affect the output. So we can write this as e to the m log base e z plus I m arg z, and it's the same thing. And in fact, I am, well, yeah, that's fine. Now, what is this? This is equal to e to the real part. And I'm actually, well, okay, we'll do one more step here. Cosine m arg z, so cosine of the imaginary part, plus I sine m arg z. Now this term here is an argument of z to the m. It might not be the principal argument, but it is an argument of z to the m. This guy here is really log base e modulus z to the m. So it's e to the log base e. This is all purely real now. Log base e to the, z modulus z to the m, and they undo each other. So we're going to get modulus z to the m, and then cosine of an argument for z to the m. Cosine is and sine are 2 pi periodic, so it doesn't matter what argument we take. So I'm going to go to little arg. And this is exactly what the polar form of z to the m is. Polar form. So my point with this sort of longer tangent is our definition agrees with the usual definition when m is an integer. It's just multiply the argument by m, which we did, and then raise the modulus to the nth power, which we did. However, if you sort of naturally generalize this, then what you get are these multi-valued functions. It happened to be this is just single valued. So anyways, it agrees with what we've been doing.